All right. Good afternoon, everyone. Let's go ahead and start. So, we are on lecture 5 today. And we're going to start off by talking about outliers. Okay, so here we go. We're gonna have some group of data points like so. And okay, I'm gonna draw a point out here. So we got this little data point that seems much higher than everything else. Okay, so raise your hand if you think that this point constitutes an outlier. Okay, most of the class. How about now? What about this point? Still an outlier? Raise your hand if you think it's still an outlier. Okay, and how about now? Still an outlier? Okay, like half the people don't think it's an outlier anymore. Okay, so yeah, there is some subjectivity to this question of like what's considered an outlier and whether or not it's us kind of just looking at it visually and being like, oh yeah, I think that's an outlier, versus if we are to make some kind of judgment call statistically, you know, you're still technically always making an kind of assumption or an artificial threshold or cutoff to dictate whether something's an outlier or not, okay? And so, you know, what I just asked you guys to do in identifying an outlier visually, you know, we're gonna come up with some statistical methods to determine an outlier, but really, you know, the threshold is just as arbitrary as you guys raising your hand and voting and deciding whether something should be considered an outlier or not, okay? And I will say that right now what we are talking about is identification of outliers and not treatment of outliers. Okay, so there's a different question about what we do about them compared to whether or not we, you know, figure out whether something should be classified as an outlier. So outlier analysis. So this is a data point that differs, let's say, statistically from other observations. Okay. There are a couple of ways that are kind of standard operating procedure for identifying an outlier, or at least measuring, well, I should back up. Different procedures for measuring the impact of any particular point, which is what lets us identify via a arbitrary cutoff that something is an outlier. Okay, so the first one is known as leverage. So how much would predicted value change if the observation were shifted 1 unit in the y direction? Okay, that is the formal definition of leverage, and leverage is always between 0 and 1. Okay. There we go. All right. So the way we calculate leverage is HII is equal to DYI predicted over DYI. So the change in our predicted value from changing the actual value of an individual data point. Okay? And I'll show how to implement this in just a second. First, we're just going to go through the definition of the other one, and then we'll look at implementation in R. So leverage is one example of how to do this. And the other is influence. So this is the effect of deleting the point. So in both of these examples, we take any observed point and we perturb it in some way, and then we measure essentially what happens to the model. This is also known as Cook's distance. So in Cook's distance, the way that we do the perturbation is we get rid of the point, and in leverage, the way we do the perturbation is by going up and down in the y direction. And they will both give slightly different results depending on where our outlier is in the sort of overall cluster of data points. Okay, so again, kind of just reiterating in general with this class, we are not as concerned with memorizing these equations, and these are mainly here for reference, and to help us understand sometimes particular effects as they relate to the equations. And this term here is the fit without yi, and that's how we essentially get rid of the data point. And k is the number of coefficients. So you'll notice like the Cook's distance will actually, the Cook's distance will increase as the fit changes when you get rid of your data point, right? The numerator will grow because the difference between our fit with and without the points is larger. And Cook's distance will decrease with the larger number of variables. Oh, hang on. Apple is doing this thing where it's like trying to correct my writing, and then it makes it look even worse. So this is number of coefficients. Okay, just leave it. Okay. Any questions about either of these or outliers in general? Okay, in which case, let's take a look at how we would generate these results from R. So, sure. In here?
Yeah,
You, zoom in. Whoosh. No, just kidding. Like,
so it's just like y hat.
yeah, sorry. Y hat sub j, and I'm using j instead of I because there's an I indicator for which point that we're actually dropping out. So the numerator just is fit minus fit without that I. Yeah. Okay, so we are going to do this thing again. This is our typical data sets. All right, so let me run all this stuff. And here we are again, right? So this is, yeah, the same kind of plot. Well, not the exact same because we're doing random selection or random draws, but basically the same random set of data points we've been using. And what I'm going to do now is I'm going to add a single outlier. So to my x, I'm going to append a single data point. So x is going to be, I'm adding x equals 100, and y is going to be 20. And if I plot this again, we'll see where that outlier shows up. Okay. So I replot everything, and then now I have this crazy point way the heck out here that's likely going to influence my results in some way. And so let's first run the model. And see what happens. Okay. So, a couple things going on here. So our intercept, so what are our true values for our intercept and our slope? We've only seen it for like the last 3 classes. Yeah, 0.5, I heard, is the slope, and then our intercept is 0. Okay. When we've run our regression model, we haven't hit it exactly, but we've been pretty close, right? And we've seen, I believe in most of the examples that we looked at before, the 0.5 is within 1 standard error of the coefficient estimate, right? So let's see what that looks like here. Here, our estimate of the intercept is, okay, it's larger than 0. We never saw that it was actually equal to 0 in the ones before, but the standard error is 0.9, so it's like 1.5 standard error values away from 0, which is larger than what we saw before, still not statistically significant. And here, instead of 0.5, it is 0.438. So quite a bit smaller than we've seen before. Makes sense, right? There's like this one data point out here which is dragging the slope down. And notice that we are 0.03197 standard errors. That's the size of our standard error. So, you know, it's definitely saying that there's a slope, but now how different is this from, how statistically different is this from the true value? Well, we could do something like zero point 0.5. Let's see, 0.5 minus the slope 0.438 divided by the standard errors of 0.03197. This is almost 2 standard errors away from from the true value of the slope, right? So it is, at the 10% level, statistically different. So we would say, right, that our outlier is actually affecting our results in kind of a substantial way, in a significant way, I should say. Okay. Anyone have any questions about that? Yeah.
The difference between the coefficients are like 2 sigmas apart, then why is the p-value so like small?
This p-value here is a hypothesis that the coefficient slope that's estimated by the model is different from 0. So just to be extra clear, because I think this is a good example of that distinction. So we have beta equals 0.43, and the hypothesis is that beta is equal to 0. And if I look here, right, the standard error, standard error is 0.0312, 0.0312, and so we reject the null hypothesis that beta is equal to 0 because according to this, it's this is more than 13 standard error lengths away from 0. Yep. I am asking about a different hypothesis, which is hypothesis is beta equals 0.5. Normally, I would not be able to make this hypothesis, but right, because we know the true value, I can be like, okay, well, what does this look like, right? And so here, this is about 2 standard errors away. So you would say that it's not equal to 0.5 at the, I think that's at the 10% level. Yeah, we don't quite make the 5% level. Yeah, because it's slightly smaller than 2. Make sense? Cool. Any other questions? Is this confusing to anyone? Okay. So that's all kind of an aside. The main thing we want to look at is how to actually calculate the leverage and influence values. So we'll start with leverage. So leverage, we do hat of the model matrix, example model 1. And this will give, this will calculate the leverage values of every individual point in our data. So if I were to plot leverage, it would look something like this. And it's just going by the index value wherever it shows up. We added this last, right? And so it just happens to be the last point in the index. And here, remember, leverage is always between 0 and 1. And so I've made it really obvious, right, that you have this particular point that has a lot of leverage in this particular example, and that's like a very distinct point from the rest of these. And yeah, you may choose some kind of cutoff, right? Maybe you say, oh, if anything above 0.15 or anything above 0.2, we'll get rid of. Or sorry, I shouldn't say that. We'll consider that to be an outlier, right? But you may be in some data sets where the spread of your leverage is a lot larger, in which case, there is, again, some ambiguity to the idea that like you have one kind of threshold value for leverage that you can use to categorize something as an outlier. Okay. If I were to plot x against leverage, that would look, something like this. And so here, you're going to see something kind of interesting happening, right? And so now I've plotted all of the points in order in x. So does anyone see a pattern here? You're nodding your head. What is the pattern that you see?
It looks like a little parabola.
Yeah. So the way that I would think about this is, imagine that your data points are like organized in some way, and then you were to add your outlier so that it was at the sort of midpoint of the data. You can almost think of this as like a lever, right? Hence leverage. So points farther out along x at either ends are by nature going to have more leverage because of the way that this is defined. As I move points up and down, so, okay, if I were to jump over here really quick. Okay, if I have a bunch of data points like this, so if I have an outlier here versus an outlier here, and then I'm adding these leverage points, right? The ones that exert kind of more, it's kind of like torque, right? The ones closer to my extreme ends will exert more leverage than the ones closer to the midpoint of my my overall points. And that's why you see this type of pattern happening. Okay? So just know that there is some fundamental relationship between the leverage and the location of the data points that doesn't actually have to do with how different a data point looks from the rest of the data. All right? The other one is Cook's distance, right? So this is influence, and you can just use, there's literally a function called Cook's distance, and we just put in our model. And we can see what that looks like. And once again, we've made it abundantly obvious in this case. It's very apparent that it looks very different from everything else. Note that Cook's distance is not like leverage in the sense that it doesn't index between 0 and 1. It is dependent on the sort of context of the values and the magnitude of the numbers in your data set. Okay. So those are the two primary ways that we identify outliers. And I'll once again emphasize that that is a separate procedure from deciding what to do with an outlier. And so people have different philosophies. Oh, yes, go ahead.
Before we jump into that, I'm having a hard time understanding the definition of influence and looking at this graph.
Okay, sure.
Because the effect of deleting the point.
Yep.
How does that?
Yep.
So if I delete the
So-
outlier all the way at the top.
Yeah, let me show you. So I'm gonna get rid of these guys here. Okay. So I have some kind of fit line that goes through here, right? And what I'm gonna do is I'm going to get rid of this point here, and I'm gonna recalculate my fit line. And now that fit line looks something like this, okay? I'll add that point back in, and now I'll get rid of a different point here, and I will recalculate the fit line. And maybe that will look something like this. So, what the Cook's distance actually does is, okay, for this, I'll change the color actually here. This one will be green. So for this one, where we got rid of this point, and that corresponds to, okay, I should have just had these colors like this in the beginning. Okay. Okay, so this this point that I eliminated corresponds to this line here and this line here. So we're going to call this alpha. Oh, okay. We'll call it A and B. A and B. That's at that's corresponding to this. So the idea is, what is y hat A minus y hat B squared divided by k MSE. And then you do that, you repeat that for every other point in this data set. So here, 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 here. And we add all that up, and that calculates out to your Cook's distance. And you can imagine that for the one that's like here that we got rid of, if the line looks like this and then the line changes to like this, then this value will be a lot bigger, right? So that's what, does that help?
This is great.
Okay. It just looks like a bunch of scribbles to me, so sometimes hard to say. Yeah, so that's the intuition behind how this gets calculated. And then the point that has the large Cook's distance is going to be the one corresponding to the one that made the fit change a lot, hence is the one that had a lot of influence on the model, which is why this is also known as influence. Okay? All right, back to the philosophy of outliers. And different people are going to tell you different things. There is, some schools of thought where, okay, we've identified the outliers and the best thing to do is to just like get rid of them and then run your models. And you have like a clean model free from the influence of these sort of outliers. And I'm like not going to say that that is necessarily wrong, right? That is one way of kind of viewing the way that you decide to do your data analysis, and there's always like subjectivity to these things. What I would say is that to the extent that these data points or any data points that you stumble on are part of the real sort of data generating process. And when I say data generating process, I mean like that data comes from some, real, observation, right? It's not, it is like part of the data set, even if it looks weird. And that I think you ought to treat these things a little bit more carefully. Oftentimes, we think about running the models with the outliers and caveating some of the results, with the fact that we know that there are some observations that look a little weird, or running both with and without the outliers and understanding kind of the influence and effect of having the outlier included, right? And so I would not encourage you, like even if you were to decide to get rid of outliers in doing a particular analysis, I would encourage you not to do so like mindlessly, right? Why is that data point there? What is behind the data generating process that led that outlier to be in the data in the first place? And like, does it warrant kind of special recognition in ways that we talk about it when you do analysis? Okay, so I would just encourage you to be thoughtful about the way you treat outliers in analysis. And there is no like, again, there is no like formal sort of treatment method for dealing with this, outside of just like deleting them, which I wouldn't necessarily encourage you to do all the time. Okay, any questions about that? Great. In which case, we are going to add some dimensionality to what we've been talking about so far. So, I think a lot of the way that I've organized this class is we kind of start with the basics and we just like layer on more and more complexity. And so we've gone through, I would say, kind of the basic foundations of linear regression so far. And so the next kind of peeling back of the onion is thinking about multiple regression. Multiple regression. Okay, and so this is an extension of simple linear regression. To predict the value of a variable based on the value of two or more variables. Okay. And so that could be anything from, let's say, yi equals beta 0 plus beta 1 x1I plus beta 2 x2I plus our error term all the way to yi equals beta 0 plus beta 1 x1I plus beta 2 x2I plus dot 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 beta n minus 1 x n minus 1 I plus beta n times x and I plus our error term. Okay, so anywhere from 2 variables to generically n variables, right? And so that really could be specifying any of kind of any size, right? And so when we think about what this does to the way we visualize our models, right? So we've been, I think, right, one of the fundamental nice things about starting with these univariate linear regressions is that a lot of the visualization of the concepts that we're talking about are a lot easier. And as soon as we start introducing more and more variables, that visualization becomes harder, and our ability to do comprehension is a little bit more challenging, which is why we want to really get it right for the 2D stuff before, you know, we talk about what that looks like for, you know, 3-dimensional things. So this would be kind of my representation of data points in 3D space, where the size of the dot is larger if it's closer, and instead of a line, we would then have kind of a plane going through these data points, right, in 3-dimensional space. And your ability to kind of visualize all of these things immediately becomes much harder, even just adding one extra dimension. I'll add a word of caution, which is that what happens when I gets closer to n. So the number of data points versus the number of parameters, right? So we can actually think of this in the context of even in the univariate. So if you have three data points, I can fit a line through here. If I have 2 data points, I can technically still fit a line, but if I have 1 data point, I cannot fit a line through it. And so you need to have at least the number of points equal to your degrees of freedom. And if that's the case, then you will have a perfectly estimated model because all of the variability is perfectly captured, right? So that would be, in this case, I would have to have 3 data points. to form a plane. And so this can be a common thing that happens. Well, I wouldn't say it's very common, but if you have a data set that doesn't have very many rows but has a lot of columns, has a lot of variables, you may start to run into these issues, like singularity issues, where you don't have enough variation to explain across all the dimensions of your variables. Okay, any questions? So let's take a look at implementing this in R. Okay, so multiple variable regression. So we'll have x1, we'll have x2, we'll have x3, and we'll have x4. We'll have our error term, and then we'll define our y multi as 0.5 times x1 plus 2 times x2 plus our error term. Great. And it is always a good idea to kind of understand the relationships between variables, right? And so definitely would still encourage you guys to visualize your data as much as possible. In this case, we're like, oh, well, there's only like 4 variables, so I can go ahead and visualize what each of those variables look like relative to my y. So we'll do that here. Hang on. I need to change the size of this. No. Okay, 1 second. This is what happens when I blow up the font for you guys. It can screw up the plotting sometimes. Okay. So in this particular example, I am plotting each of my x's against what the y's look like. So who wants to tell me about what they see here? Raise your hand if you think it looks like x1 and y are correlated. Okay, raise your hand if you think x2 and y look like they're correlated. Okay, x3, x4. Okay, cool. So Yeah. It is still important to understand by visual inspection, right, where it's possible, always a good idea to go in and kind of look at those relationships. And here, we're saying we think that x2 looks like it's like correlated to y, and so when I run a regression, I would at the very least expect x2 to be to have some kind of relationship in that regression with y, right? And that's reasonable. What variables actually are correlated to y? X1 and x2, right? Because we know that because we said that right here, right? Y multi is 0.5 times x1 plus 2 times x2. So that means visual inspection, especially when you're coming to multivariate, is not going to be able to exclude variables from having some kind of correlation, right? It just so happens that x2 has a more dominant effect on the variation in y. Thankfully, so let's run the model. Y multi regressed on x1 plus x2 plus x3 plus x4. So I'll run the regression, and we'll run the summary. Okay. Volunteer to help me interpret these results. Who wants to like walk through this table with me? Anyone? Yes. So intercept value.
Negative 0.5, but it's not significant.
Okay, and then x1.
X1 is about 0.5 and it's significant. X2 is about 2 and it is significant. And it makes sense because
Yep.
we hard coded it. And then 3 and 4.
About
Close
zero.
to 0.
Yeah.
Not significant.
Yeah, exactly, right. And so thankfully, the regression is, very, very powerful in understanding the influence of the data and the relationships, more so than we would be able to from eyeballing the data. And it is able to extract very close to what we know the true values of the betas are, right? Which is that x3 has no influence, x4 has no influence. These are both close to 0 and are statistically not different from 0. And we can see that here. Whereas x1 is about 0.515, which is very close to 0.5. x2 is 1.98, and they're both, statistically significant. The standard errors, the standard error is within one error for the actual true value, which we know, which is great. And same for, that's right? So it would be 0.014. Yeah, so it's within one standard error of x2 as well. Okay. Any questions about this? All right. Yes. Yeah.
How come the graph still looks like that, even though
Yeah.
even though it shouldn't? I don't know.
Well, no, I mean, it is what it is, right? I think the point of me adding this graph is to demonstrate that, like, when you have a mismatch in the amount of variation captured by a particular variable, the influence of that thing could be swamping the influence of other variables. So x2 explains variation in y. x1 also explains some variation in y. But the amount of variation covered by x2 is a lot more than the variation covered by x1. And so we haven't taken that variation out in y when we graph it against x1. And as a result, it looks a lot more random. And so x2 is essentially sheltering in that plot. If you were to, actually, let's see here. I wonder if we could control for the variation in the x2 is doing, and then replot it against x1, and then you could see what the influence of x1 would look like. Okay, I'm gonna do this on the fly here, so hopefully you can see what that, let's see if I can do this. Okay, so I'm gonna call this y minus x2. So this would be y dot multi minus x2 times 1.986, and then we plot x1 against y minus x2. I think this works. Yeah, oh, okay, hang on. Dev off. Okay. Yeah. So now, if you essentially get rid of the like variation in y caused by x2, now you see this kind of trend in x1, right? But if you don't do that, then your ability to differentiate the effect of x1 is like hidden by the greater amount of variability introduced into y because of x2 that wasn't controlled for. So that is, again, to just reiterate this point that when I look at these things visually, you have to be careful about excluding variables because the effect of x2 could be masking, or the effect of another variable could be masking the influence of a particular variable. So when I look at our original plot here, yeah, from a practical standpoint, this should be telling you things to look for, but not things to exclude from your modeling and your like model specification. Okay, so this would tell me, oh, I got to watch out for x2 and make sure that there's something happening there, but I'm not going to rule out x1, x3, or x4 yet. Okay. Any other questions? All right. Great. Yes.
Just to make sure I'm understanding, when we did that x1 through x4, those are also on your drawing the different axes, right? If we're looking at different planes.
Yeah. Yeah. So,
Cross section of those two specific axes, like y and x1, y and x2.
yeah.
Right?
Yeah, so I looked at this plane, and then I looked at this plane, and then I looked at two other planes that I don't know how to draw because I can't draw
We
on.
don't look at planes between x's. So, for example, x1 and x2.
So yes, actually you can. Yeah, so
If that's like
no,
part B and we're in part A, then
no. Actually, I don't talk about this in this class, although maybe I should. So, this is actually an important concept. So this would actually be kind of like looking at this plane, right? So let's suppose I have data that looks like this. And then let's suppose that I have data that looks like this. So in the example on the left, I have data that's like very uncorrelated. And then on the data on the right, I have data that looks very correlated. What does that mean for the regression? So let's think about this conceptually. Y regressed on x1 and x2. Here you may have variation in y that corresponds to x1 or variation that corresponds to x2 or maybe both to some extent. And the idea is the model will be able to like pick that out as it relates to the individual correlations with y and x1 and y and x2. Okay, so maybe that explanation is maybe not as clear, but let's look at what it would mean for the second example, and then I think it'll be a little bit clearer. So here, if I have y regressed on x1 and x2, and you happen to see an effect, right? So that there is some kind of relationship between y and x1 or y and x2. Would I say that that effect is because of x1, or would I say that that effect is because of x2? I don't actually know, okay? Because x1 and x2 are so closely related. And so is it that as x1 gets bigger, I see the effect, or is it as x2 gets bigger, I see the effect? This is known as multicollinearity, right? The problem is the same variation is explaining the variation in y, and therefore I don't know which one I should attribute it to. And so typically when we run into this issue, the model is going to have a hard time differentiating, and it'll just say that it's one thing versus the other. And so oftentimes the strategy is to like drop specific variables that are highly correlated with one another so that you don't run into this issue. Okay? Would I know how to draw that here? So that would be, yeah, okay. So that would look something like x1, x2, and y. And then you would have just like so this would be perfectly collinear between your x1 and x2. And I could draw a plane that looks like this. Oh my god, I don't know if I'm going to be able to draw this in a good way. Right? Or it could look like, okay. Right? If it's just a line, then I could spin the plane around in a circle, right? And the degree to which the plane spins is the model arbitrarily making a choice of how much it's getting influenced by x1 or x2. And the more multicollinear it is, the more arbitrary that like plane would spin around those points. Okay? It is just kind of arbitrarily deciding if x2 is more influential or x1 is more influential. And so we consider this to be kind of problematic. And so in cases like this, you just drop one of the variables. And that will more relate to like a more qualitative examination of what variable you think makes sense to keep and to drop. Does that answer your question?
Yeah, I was curious about that.
Yeah. It's actually, it's an important concept. Maybe I should add this to future lectures. Multicollinearity is a very common thing to deal with when you have, variables that are correlated, and you have to make some kind of judgment call about when to keep it and when to drop it.
Can you drop one of the variables, just like flip a coin, whichever goes first?
No, I mean,
Drop one and then drop the other.
yeah, so typically, there are a couple of ways to make that judgment. You might look at the individual correlations between x1 and x2 and y and keep the ones that are higher, right? So, if you have x1 and x2, they're correlated by like 0.8 or something. You're like, oh, that's really high. These are going to be multicollinear in my model. Let me look at the correlations between x1 and y and x2 and y, and maybe I'll keep the bigger one. That's one way to think about it quantitatively. Qualitatively, you might have, like some, you may have some inkling of like what variables you want to keep or omit as it pertains to like a study of something that you like understand where the mechanism might be more closely related, and so you would want to get rid of the one that's like not as relevant. So like let's say, I don't know, like you wanna see how much it's raining, and then you relate that to people carrying umbrellas versus wearing like rain boots. And then rain boots and umbrellas are like correlated high enough that you would want to get rid of one of them. And maybe we generally know that people will have umbrellas more than they'll have rain boots, and so you choose that one instead. I don't know. This is kind of a weird example, but yeah. So it's like you're making judgment calls, less, less so on the like quantitative part and more of your like understanding of the data and the relationships in the data. Okay, yeah. So little aside, but I think an important one. Any other questions about this? Okay. Next thing we'll talk about is when we're talking about a linear regression, it means that the model is linear in parameters. And so we like to think of this as like the relationship between your y's and x's are these kind of straight lines, can be described with kind of straight lines. So that does happen in kind of nature, but a lot of sort of natural data also comes in the form of like exponential relationships, right? So you think of like exponential growth curves, that type of relationship is just as common, if not more than common, for like linear relationships. And as a result, there are there are ways in which we take data that doesn't look linear, and we can fit specific models to it, and we'll talk about that later. Or we can take data that doesn't look linear and linearize the data so that we can apply them with these sorts of linear models. And so because exponential data relationships are so common, that is one of the most common practices that we'll see practiced in linear regression is transformation of exponential data to look linear. Does anyone know how to actually do that? How do we linearize like exponential looking data? Log, exactly. So you just apply a log transformation. And so that's done so in such a common way that there's this kind of unique property that we'll talk about now that's kind of exclusive to these like log transformations. So we're going to interpret log x. Oh, and I should just mention, I'm going to say log a lot right now and for the kind of rest of the class. And when I'm talking about log, I'm talking about natural log, not base 10. Okay, so anytime I say log, just pretend I'm saying natural log. Okay, so what we have looked at is sort of classified as level. So this is like y equals alpha plus beta x plus epsilon. Okay, and so we interpret, right? We know how to interpret this. The change in y is equal to beta times the change in x, right? So if x goes up by 1, then how much does y change? By beta. Exactly. Right? That's just slope, right? So x goes up by 1, that's our rise, and then, that's the run, and then the rise is equal to beta, which is the slope. Okay? Straightforward so far. I think everyone should be comfortable with this at this point. So we can do transformations of our data and still maintain that in the structure of these like linear regressions. So we're going to look at the different ways we can do that. So log level. So this is ln of y is equal to alpha plus beta x plus epsilon. Okay, so it turns out that doing this actually still lets us do interpretations against the like raw values of y. And let me describe what this looks like. So we're gonna modify this just a little bit, and you're gonna say the percent change in y is equal to 100 times beta times the change in x. So basically you're saying as x goes up by 1, y goes up by 100 times beta percent. So you can do a percentage change in y as x goes up and down. Okay? Has anyone seen this before? No. Okay. This is like very common in econometrics. Okay, I saw you raise your hand. Do you know why we're allowed to do this? Yeah, okay. No, they teach this in econ all the time, but I feel like they never show why the interpretation is allowed to be this. Yeah, do you know?
Checks the elasticity
Mm-hmm.
of the changes made by the variable.
So elasticity is like percent by percent. We're going to talk about log, right? So that's, so yes, but actually what I'm asking is we interpret it as percent changes, which enables us to think of this in terms of elasticity, but why are we allowed to think of these as percent changes? It is a totally convenient coincidence of math that allows us to do this, which is ln of 1.01 is equal to, or yeah, you guys didn't know Apple could do this now. They like touted it. It's really annoying because I don't actually want it to solve. Okay, all right. Shall we see? Okay, yes, thank you. I was gonna write that, but okay, it did it for me. So ln of 1.01, so in a marginal change of the value is very close to 0.01. It's close to, right? So you're basically saying if you natural log a marginal change in 1 unit direction, that change is about equal to 1%. And so because of that coincidence, that has enabled economists to be like, when I do these log things, I can now say it as an elasticity. It's because of this property. But it's not exactly equal to 1, right? And so just be careful. This is really technically only for marginal changes. Okay? Okay, so then we can do the same thing for level log, which is y is equal to alpha plus beta log x plus epsilon. This is delta y is equal to beta over 100 percent delta x. So as x goes up by 1%, y goes up by beta over 100. Okay? And the last one is log. This is ln of y is equal to alpha plus beta log. I'm writing ln's and logs, but okay, they're all ln's. Sorry.